Alright, in this video we're going to simplify radical expressions, and the goal here is not to show you every possible situation you're ever going to run across. It's to give you a few examples and ideas that you can use while you're solving or simplifying more and more complicated radical expressions. So again, this does not cover everything, hopefully just gives you some tools to work with. Alright, the first one, we have the square root of 288. I know 288 is not a perfect square. So what I'm going to do is I'm going to break it down into its factors. For example, I know 2 divides into 288, and that becomes 144. Now, hopefully, the idea along the way is that I do find perfect squares. For example, 144 is a perfect square, so the square root of 144 is 12. So I'm going to put that on the outside of my radical. I'm still left with a 2 on the inside, so I still have the square root of 2. And this would be my simplified version of the square root of 288. All right, now we're going to move on to the next example. Similar but different, because now you can notice I have a cube root instead of a square root. So the idea is if 108 is a perfect cube, it's simple, I'm done. But we know it's not. So I have the cube root of 108. I'm going to start to break it down into its factors. I know that to be 2 and 54. So now, don't have a perfect cube yet, so I'm going to break that down even more. So I'm going to break that down into the cube root of 2 times 2 times 27. Again, if I take all these things, multiply them back out, I still get 108. But now, if you'll notice, I get a perfect cube in 27. So 3 times 3 times 3 is 27. So now I can put a 3 on the outside. And I still have the cube root of what's on the inside, which is 2 times 2. I can simplify that back to 4. And now we have the simplified version of the cube root of 108. All right, this next example, the issue that we have with this one is this radical in the denominator. I don't want to have that. So in order to get rid of that, I have to multiply by something that allows me to move the radical from underneath the fraction. And to do that, I'm going to multiply by a 1. I know what you're thinking. You're like, wait a minute, that's the square root of 6. But if you look closely, that's just a 1. All right, so let's go ahead and multiply across and see how that helps us. So in the top part, I have 12 times the square root of 6, but now on the bottom, I have the square root of 36, which we know to be 6. So I have 12 times the square root of 6 over 6, and then if you'll notice here, the 12 and the 6 are just a regular old fraction that I can simplify down to 2 times the square root of 6. And this would be my simplified version of the original 12 over the square root of 6. Now let's look at this example here. Very similar, except now you'll notice instead of a square root, I have a cube root, right? Well, in order to have the square root of something, I need 2 of the exact same things. So here I need to multiply by the cube root of 25. But again, since it's a cube, I need a third one, so I have the cube root of 25 as well. Now, also, I can't just multiply by any number. I have to multiply by 1, okay? So now what we've done here is we've said, okay, this is just a 1. This is just a 1. So when I multiply those out, my original expression does not change its value. It just changes the way it looks. All right, so now let's go ahead and multiply everything through and see what happens. So on the top, I have 10 times the cube root of 25, but I have that squared, right, over. Now on the bottom, I have the cube root of 25 times the cube root of 25 times the cube root of 25 is just going to give me 25 on the bottom. All right, we're still not done yet, unfortunately. I can take this 25 and square it, which gives me 10 times the cube root of 625 over 25. And then just like my example up here where I had the cube root of 108, I can now take this cube root of 625. So let's do a little side work here. I have the cube root of 625. I know 625 is not a perfect cube, but I know 125 times 5 is 625. And then if you'll notice, 125 is a perfect cube. Perfect cube of 125 is 5. So I have 5 times the cube root of 5. So that is what I'm going to replace this cube root of 625 with, is this 5 cube root of 5. So now if I rewrite that now, I have 10 times 5, the cube root of 5, over 25. Now here I have 5 times 10 is 50, divided by 25 is 2. So that now then simplifies to 2 times the cube root of 5. I know that was a lot and complicated, so you may want to stop, rewatch it, and see if it makes more sense the second time through. All right, in this example, you'll notice, just like in one previous to it, I have a radical in the denominator, which is something we don't want. We want to do what's called rationalizing the denominator, and that's so I rewrite it without the radical down there. So I'm going to get creative on this one, and I'll show you how this works in a sec. But I'm going to do square root of 5 plus 1 over the square root of 5 plus 1. A little different than before. I'm not just going to multiply by the square root of 5 because it's not going to help me. You can try it and you'll see why it doesn't. But here, I get clever. Let me show you why that works. Because when I distribute the 1 to both of those, I end up getting square root of 5 plus 1 in the top. And now I'll show you why I've chosen to use the same or a similar term, but instead of the minus, I make it a plus. Here's what happens. It becomes what's known as a difference of two squares. For example, I multiply that out. I get the square root of 25, which is just 5. And now I've got the square root of 5 times plus 1, which is plus square root of 5. Now I do this next term and I get minus square root of 5. And what happens is I end up getting a 0 pair right here in the middle, which is something I don't have to write. Right? So now the reason I've chosen to use this similar term that's in the bottom, similar binomial that's in the bottom, is because I have a plus and minus version. It's so I can get that 0 pair, thus having the radicals kind of sort of take care of themselves and not be in the denominator. And then I need to distribute the last term, which is negative 1 times plus 1, which would be minus 1, which simplifies into square root of 5 plus 1 over 4. And that would be my simplified version. And again, it's simplified because I no longer have a radical in the denominator, and that process is called rationalizing the denominator. All right, I hope this video helps, and utilize these tools and these methods to help you simplify radical expressions. I'll see you in the next video.